Explaining Denali's number 1, which includes the extended Bernoulli, which is topic 3, and momentum balance, which is topic 4. In this problem, we have water flowing through a shower nozzle. We're given the entrance gauge pressure and the frictional head loss, and we want to find velocity of the water exiting the shower head and the extracted force holding the nozzle in place. So what we assume is, as she states, steady state, incompressible, so that's constant density, it's adiabatic, there's no change in G, and that there's no work. So we go and we set up this energy balance right here, and Z1 is equal to Z2 because there's no change in Z, so we can cancel those out, and when we take P1 minus P2 to put it over on this side, we get P1 gauge because P2 is atmospheric. So then we can find V1 over here from the flow rate, and then we know the frictional loss, so we use all these other numbers to find V2. We have a x-directed momentum balance, which we are doing in minus out plus generation equals accumulation. So then we have beta times mass times velocity going in to the shower head nozzle, and then we have that same thing coming out. Then we also have pressure forces coming on in and out, and then we have the force of bolts, which she defined as in the negative x direction, holding it there. And then we know that that is going to equal 0 because there is no accumulation. The system isn't accelerating or changing mass, so that's 0. And from there, it's really just plug and chug. We know the mass flow rate can be calculated from our volume flow rate. And then since the answer is positive, we know that our directional guess was also correct. Denali's number 2, which includes hydrostatics, which is topic 1, and buoyancy, topic 2. So this problem, part A, you drop your phone to the bottom of the lake and want to find the absolute pressure on it at the bottom of the lake. So you just use the hydrostatics equation, which is that P2 equals P1 plus rho GH. P1 is just atmospheric, which was standard atmospheric pressure of 1 atm or 101.3 kPa. And then you know your density of water, G is standard, and H, because we are assuming constant density, constant gravity. Then in part B, we're finding the buoyancy force acting on a kayak, given the mass of the kayak and the person. So again, you're assuming constant density and gravity. So you use your buoyancy force equation, which just states that your force of your buoyancy equals your weight, which in this case is going to be the total mass, which is your kayak plus your person times G. So that gives you your buoyancy force. And then in part C, you calculate the volume displaced with the person in it, and then when they jump out. So you find this by setting this force buoyancy equation equal to rho times G times the volume displaced, and that's just a standard equation. And so you do that when you have the person in it, and then when you have the person without, and then to calculate the difference, you subtract the two volumes.